Good afternoon again. I started recording, so we can start the lecture. First of all, we are already almost at half of our joint experience, so time runs very fast. So we are moving forward with the calendar that you know, which is available on my website. I got a question here in Ravenna from, what is your name? A namer? Nemran, okay, about the exam dates. So in principle, formally, I could not make any exam before the official end of the lectures, which is June 9. It is a Friday. So for the other courses that I'm teaching, I'm scheduling the exams after starting from June 12. There is to say that you are only 2 students because given that we are finishing the lectures in advance, I think I can check with Professor Archetti whether it would be possible to make the exam earlier for you, but please be aware that if we make it earlier, like in May, we cannot register it until June. So I'll check with Professor Archetti. If it is fine for you that we make the exam earlier and then you wait for the registration, that's okay. Anyway, I will check with Renata and then I'll tell you, okay? Very good. We will make our best to accommodate, given that, you are 3 students, I think. So I think in principle, it may be possible. Okay, now let me just go to the website and I want to make a brief recap. Last time I talked about Harbour oscillations. I think it's an interesting topic. And then I passed to an exercise, computation of mooring forces. The exercise is done with R. Do you know R already? Do you have already? No. Okay. Okay, that's fine. So I made first an introduction to the software. It's in the video, and it is similar to MATLAB. Do you have any knowledge of MATLAB? Yeah, it is very similar. I mean, the philosophy is the same philosophy, and the language is very similar, but of course there are differences. R has the advantage that it's completely free. It's public domain. And so this is why I am using it. Also because I just want to give you an overview of a different solution, of a different possible solution. So then I started the exercise, but the exercise was not concluded. So I'm planning today to dedicate some time to computation again. We may finish the exercise, but I would like to make it in the second 2 hours. And now I would like to go back to, let's say, theory, let's call it this way. First, I want to say something more about Harbour oscillations for 2 reasons. First, it is the first time that I give this lecture, so I was not really very happy with my performance last time in terms of clarity. So I want to give you some additional information. And also I updated the web page, the lecture here, the written lecture. So I take this opportunity to say something more about Harbour oscillations. First of all, it is an important topic. Let me be very clear. It is not very relevant for our region because oscillations, they are called oscillations, a kind of waves that have a very long period. And this is why they are called oscillation rather than waves. Also, there is an intrinsic meaning of oscillations, which is the possibility that a resonance is created. Oscillations typically, we refer to oscillations for closed basins or basins that are open on one side and which are excited by waves incoming from the sea, from the ocean. And when we talk about oscillations, implicitly we admit that there is a chance that a resonance effect is triggered into the closed basin, which ends up with amplification of the waves. So this means that a wave with a very long period, we will see why long period, a wave with a very long period and maybe limited amplitude may come from the ocean to get into the harbor and get progressively amplified to the point that it causes significant damage, like rupture of breaking of the mooring lines, impossibility to make any management of load and unload from ships, and physical damage to infrastructures. This kind of amplification, as I said, it's called resonance. And probably you have heard already in other courses, in your bachelor or here in other courses of structural mechanics, for instance, what is resonance. So this is, as I said, something that is not very relevant for our region, because our region is less subjected to waves with very long period. And also our region in general, it is not exposed to coastal flooding. The only exception, if we talk about our region, is Venice. When we hear about the Acqua Alta in Venice, which is high water, the high water is caused precisely by a long-term oscillation, which may be caused, this long-term, long-period oscillation, which may be caused by wind, may be caused by meteorological conditions. I mean, the phenomenon is not very frequent, but it is potentially dangerous. It is potentially dangerous because, as we will see, it may cause some unexpected conditions, some unexpected flooding. So when do we talk about oscillations? As I said, they are caused by resonance. I think I have the PowerPoint, but I used it. There is a PowerPoint in this lecture, but I used it last time, and I just want to give you some additional information here. So I go by links in the web page. These oscillations are caused by resonance. They may have different names. We can talk about Harbour oscillations, but they are also called Harbour resonance, Harbour surging, and it is also called this phenomenon seiching. With spell, the oscillations are also called seisich. The spelling is what you see on the screen, S-E-I-C-H for the singular, and with an A-S, a final A-S for the plural. Some pronunciations, some people pronounce the term as seix. I think the correct pronunciation is seiche or seichis. It is a term that probably is derived by the Latin, and last time I said that these seiches were first observed already in the Middle Age, because, for instance, we got a report of an episode of lake seiching in the Lake of Constance in Switzerland, and also later on in the Lake of Geneva. Seiching is well known for the Great Lakes of the United States, where indeed there are sometimes. Yeah, you're right, Shade. I forgot to share the screen. I'm sorry for that. Here we are. Thank you for letting me know. Okay. So these may occur in lakes, indeed. They may occur in harbor. Seiches may occur in harbor, may occur in lakes, may occur in canal. And also, in particular situations, they may also occur in open sea coast. So, to give you an example, let's, because I added some video, to give you an example, they can also be caused by tsunamis. And I show you quickly one video. First of all, for Seychelles, there is a link which describes, which brings to a Wikipedia page, but it is not really relevant. There are also other links to resonance waves. They are not very relevant. The video, I think it is interesting. It is related, it explains how a tsunami can develop, and actually the tsunami develops after an earthquake. So it's a different story, but the tsunami may originate as Seychelles. It's not very long, but I will accelerate it. I think, let me see. While you have a look, I try to remember how to accelerate the video. Just a second. Okay. Let's put it at 1.5. Should be at 1.5 now. So you see the wave that develops, that travels with a very long period, towards the coast. And in this case of this tsunami, the forcing is just an instantaneous forcing, it's just a pulse. Usually, Seychelles become more dangerous when the forcing is periodic. In this case, it's not periodic, it's just a single wave that is originated. But the forcing may be periodic. Okay, we can close this. Just 1 second. Good. And so to give you some more information, Lake Seychelles are described in 3 links here. Let me open them. So, and this is a clear explanation of how in a lake a Seychelles can form. We have wind, which displaces the water and brings the water to the other extremity, the other end of the lake. And then when the wind stops, water comes back. And therefore, there is a long oscillation, which for the Great Lakes of the United States has a period of about 7 hours, maybe from 7 to 14 hours. It depends on the conditions. And the equilibrium is restored after friction has exhausted the additional energy that the water gained. So basically, Seychelles decay exponentially due to friction, but given the high amount of energy that is involved, and given the long period of the oscillation, then it may take several hours before the equilibrium is reestablished. And given that the phenomenon is quite slow, and the rise of water occurs with a very low speed, the phenomenon is dangerous. And so some people reported that they saw the water that was going up, and lasting for a long time. This is what occurs basically in Venice, where the lagoon is like a closed lake. And therefore, you know, the wind setup may bring the water into Venice and keep the water there for a long time. So this is one discussion, and here there is another information. Oh no, this is the same link. Sorry, I think, okay, I need to correct it. Let me see. Yeah, the same link, but the third one should be fine. Okay, here there is another explanation and about the Seychelles on the Great Lakes, and you can see the same mechanism here. And keep in mind that, let's go back to the previous link, and then I need to make the correction. Wind usually is not periodic, but if you imagine, if you think of a situation where wind is intermittent, and when the wind stops, water comes back, and if you think of a situation of wind starting again, when the water, after coming back, is starting to run again in the opposite direction, you understand that in such a situation, the displacement of water may be exacerbated, may be increased, because the system has gained additional energy. And even without any additional forcing, the system will continue to oscillate for some time. When there is one of these oscillations, if wind starts again, the system gains additional energy. And therefore, the combination of the energy that comes from the forcing and the energy that has been accumulated by the system may indeed increase the displacement of water. On the contrary, if the wind keeps blowing when water comes back, then the friction of water going against the wind contributes to reduce the oscillation. So you understand that if a forcing is periodical, there is an important feature that we need to check, which is the frequency of the periodicity of the forcing, the frequency of the forcing, which we hope doesn't match the frequency of oscillation of the water body. And usually a water body has an inherent period of oscillation, which is a feature. It is an inherent feature of the water body. So when I said in the Great Lakes is about from 7 to 10 hours, you get already an implicit admission that this frequency, this period, which they are the same thing, is an inherent feature of the water body. Of course, it may change depending on the conditions, because friction may be different in different seasons. And also, you know, the forcing may have several different directions. So depending on the direction in which you trigger the oscillation, you have different periods. But still, this is a feature, a proper feature, an inherent feature of the water body. So, as I said, we have to check that the frequency of the periodicity doesn't match, sorry, the frequency of the forcing doesn't match the natural, let me call it natural frequency of oscillation of the water body. This is what we said last time. And you can imagine a situation with a pendulum. If you think of the pendulum, if we bring it out of equilibrium, because we take the pendulum in a position that is not the neutral position, and we release the pendulum continues to oscillate for some time. And there is an exponential decay of the amplitude of the oscillation. But if when the pendulum gets to one of the extremity, one of the tops, I give an additional forcing to the pendulum, then the pendulum amplifies its oscillation. If I don't give the forcing at the right time, but I make a mistake and I give the forcing to the pendulum when the pendulum is still traveling towards my hand, then I slow down the oscillation. So we have to check that in Harbour's there is not this match of the forcing of the periodicity of the forcing with the inherent periodicity of the water body. This is what I explained last time. And now let's, after I gave some definitions, which I think we can avoid here because they are very trivial. Closed basin, open basin, you can have a look at it, and I already discussed them last time. Let's try now to better understand how we can make this check of matching frequencies. And first of all, let me show you what happens when we have this matching of periodicity. This video was shown also last time. Just 1 second, because we need to wait for the advertisement to stop. And it's still 3 seconds. This is created into the lab. You see that there is a wave generator, and there is a frequency of oscillation of the waves. And here they are generating the waves with a frequency that is precisely the same natural frequency of oscillation of the tank, of the pool. And you see that there is a progressive increase of the amplitude of waves. And there is an interesting thing that you can see in this video, which I discussed last time. Let's go back some seconds. Here you see the wave travelings, the waves traveling. And then when it starts to amplify the oscillation, you have the feeling that the velocity of the wave slows down. And you have the feeling you see here that the waves are just going up and down and no more traveling towards the end of the pool. There is still some movement towards the end of the pool, but it is much slower. What they generated here, it's called a standing wave. You see that there is no more traveling. It's called a standing wave. We will see how this wave is generated. And now they turn off the wave maker, the wave generator, and you see that the system, this is important to understand resonance. The system continues, the standing wave continues to oscillate. This oscillation continues in time. And then, of course, after a while, there is a dampening, there is a release, a dissipation of energy through friction, which means that after a while we get back to equilibrium. And here you see that they are, but still it continues for a long time. And so why there is this continuation? Because the wave generator gave energy, generated energy, and gave this energy to the water body, and the water body keeps the energy even after stopping the wave generator. This is an important concept that we have to take into account if we want to understand resonance. Okay, let's go back. So, hydrodynamics of these seiches. First of all, it is a complex problem, and we need to refer to simple conditions. Simple conditions, which may be, for instance, a basin with rectangular shape, an harbor with rectangular shape, better if it's long, more long than large. And we need to refer to the situation if you want to get a description, a simple description with no friction. And so usually this is what people do. Still, the hydrodynamic model is not easy because you have to apply conservation equations. You have to apply conservation of mass. You have to apply also conservation of momentum in order to describe the waves. And you may have to take into account if the basin is not very deep, indeed, you have to take into account some friction. So the description is quite complicated, and we are not describing it in detail here. Okay. What I wanted to focus on is the concept. So why this wave slows down its velocity? Why it looks like a standing wave? And you know, I want to focus on the geometry of the system, and not on the dynamics. There are several studies, several textbooks also discussing the dynamics, the hydrodynamics of it, but I think it is too much for us. Now, how can I then describe this phenomenon? Let me refer to, first of all, let me recall the concept of reflection of waves. So what happens to a wave entering into an harbor and reaching the head? What happens is shown here. The blue wave is the incoming one, which generates a reflected wave. If you admit that there is full reflection, which means that the wall is vertical, the wall at the head is vertical, there is no dissipation of energy, full reflection means that the wave that goes back, the reflected wave, has the same amplitude of the incoming wave and same phase. So there is no phase change. What does this mean? It means that the two waves, the incoming one and the reflected one, we will see it with an animation, add each other. They sum each other. They don't cancel each other. They add each other. You don't see it here because this is a static picture. This figure, which is in the center of the screen now, it's a static picture, which means that you don't see the movement of waves. These waves are traveling. The blue one is traveling from the left to the right. The red one is traveling to the right to the left. Okay. The same situation is depicted here. But in this case, there is also the red line, which is the summation of the two waves. This is the same situation where, by the way, there is depicted the reflected wave at a different time. So this figure is hard to understand if you don't read that the two waves, the incident and reflected wave, if you don't read that the blue wave is at time t0 and the yellow wave is at time t half, where capital T is the period. And these figures show to you that indeed the reflected and the incident wave are displayed with the same line. And then they sum up here to originate the standing wave. So whenever you have a wave entering into a basin and the wave is fully reflected, what you get is a wave that looks standing, it's standing, and the amplitude is twice. Now we need to prove it, okay? And there is one more thing that I want to say. In case the boundary is fixed, then the reflection is different. So let's forget about the figure below here. Let's only look at this. When the boundary is fixed, there is no movement at the end. You can think of a string which at the end can move or not. The reflected wave has the same amplitude again, but there is an opposition of phase. There is a phase change of 180 degrees, a phase change of pi. And this situation, it's better explained by this sketch here, where you see how a boundary can be thought of being fixed. And in this case, you have a ring that is free to move up and down a pole. This is a free boundary. And as I said, the reflection is different. Okay, what I said may be better understood if we look at a video. Just 1 second, I have to find it. I think it is this one. There is still advertisement, so let's wait for it. And okay, this is perfect. Let me share also the audio of the PC. I have to check. 1 second. Okay, let's see. Just 1 second. Okay. I don't remember how to share the audio of the PC, but I think, let me just see. Cannot be here. Okay, let me try to start it. First of all, I need to activate. I think you may listen the audio through the micro. It is not really needed to listen to the audio because there are the subtitles there, so it is not really needed. Anyway, let's start it. So,
my able assistant Parker Smile, your admiring audience, and we will be demonstrating transverse standing waves. I'll also demonstrate traveling transverse waves. Here's a traveling wave. I'm starting the wave by creating a disturbance here with my hand that is perpendicular to the direction of propagation of the wave. So I'll move my hand up and down, and you'll see that the little bump in the spring travels from me to Parker and then back to me again. And you'll notice that when the wave hits Parker's hands, because he's holding it firmly, what was a peak heading toward him converts itself into a valley as it bounces off his hands. So then a standing wave is where you pick a frequency that matches the length of the string in such a way that the waves created from my side of the string and bouncing off of Parker's coincide with each other and reinforce each other to create a standing wave pattern. The lowest frequency standing wave pattern is this one. It's called mode, M-O-D-E 1, or the first harmonic, or in other words, also called the fun.
This is called the fundamental mode. I wanted to stop here because it's important. He's showing that a standing wave can have different frequencies along a string. What happens along a string is the same as for waves in the ocean. The only difference may be, with respect to our case, the fixed end or the free hand. As I said, there is a free end at the mouth, at the head of the bay, of the harbor, while we will see that at the mouth of the harbor, there is a fixed end. Why there is a fixed end? Because the position at the mouth is regulated by the ocean. It's fixed. And the reflected wave that comes back to the ocean doesn't have enough energy to displace the ocean. And therefore, it turns out that it's a fixed end. Now, he's showing in the following of the video that we can originate a standing wave at different frequencies. This is the fundamental mode. It is the most dangerous because as the frequency increases, there is also an increase of friction, and it becomes more unlikely that the frequency of the forcing is the same as the frequency of the harbor. Okay, let's try to move forward. You will see that originating standing waves at higher frequencies is much more difficult for him. It was very easy to generate at this low frequency. At higher frequencies is more difficult, and this explains if it's difficult for this person, it's also difficult for the ocean, you know? So let's see.
Fundamental mode. It's the lowest frequency mode that you can get in a transverse standing wave. If I double the frequency of that mode, I get the second harmonic, or second mode, and sometimes called the first overtone. And this one, if you'll notice, is going twice as fast as the fundamental mode. It has a node that's exactly halfway between Parker and me. That's a node where there's approximately no motion going on. So now I'm going to try and triple the frequency and get a standing wave pattern that coincides with the third harmonic, or second overtone. Try again. Okay, I think I got it approximately now. I think I had it for a little while there. It's the third mode, where the string vibrates in 3 separate segments. There's actually an infinite number of these modes that you can get, and see if I can get one of the higher modes. I think that's 4. And then if you're really, really good, you get 5, 6, 7, 8, etc. So notice that with each mode, there's a particular frequency that I have to vibrate at in order to create that mode. So 1-to-1 correspondence between the modes and the frequencies. That's standing waves.
Okay. Let's go back. And now, how can we describe it mathematically? So mathematically, it is quite simple. You have an incoming wave, which is shown here. The WI, it's the incoming wave, which we can easily describe. I will try to make a computer simulation later on to use by using this relationship here to generate an incoming wave. And then this is the reflected wave. And the reflected wave, you see that it has the same amplitude, or let's say the symbol is different, but we assume that they are the same, like here. We assume that HI is equal to HR, which is half of the amplitude of the standing wave that we are generating. And we have also a plus instead of a minus, because the reflected wave is traveling in the opposite direction. And then we just have to sum these 2 waves to generate the standing wave. Basically, we get this configuration, but let me now look at the animation here. So what you see here, let's look at this picture, which now we will try to generate in the PC. You see the green wave traveling from the left to the right, and the blue wave traveling to the right to the left, and they sum up in the red standing wave. And you see that we have a free hand on the right. This is the head of the bay, and a fixed hand on the left. Okay. It is interesting, and it's a bit of fun to try to generate this figure here with a software. At least an approximation. Let's see if we can succeed in doing that. Here there is another animation, you see, and this other animation, before I go with the software, let's look at this one. This other animation is interesting because it is shown here that there are points, coordinates along the string where you have the max amplitude, and there are coordinates where there is no movement, like the guy said in the video. The coordinates with the max amplitude, the max oscillation, are called antilodes. And the points, the fixed points, are called nodes. Everything is written in my notes. Now, there is an important thing to say that I didn't say last time. The important thing is that if you make a very simple mass balance here of the Harbour, you realize that there is a movement of fluid in the Harbour. There is a movement of fluid associated to the standing wave, because when you get a through, you have like a compression of water, and therefore water is pushed in the neighborings where there is a crest. And therefore, there is a displacement of water, and the nodes are the point with no vertical movement. But in the nodes, in correspondence of the nodes, you have the highest horizontal velocity. And this is important for us because this means that currents are originated into the harbor, especially in the transitional phase, during the formation of the standing wave, you have a considerable displacement of water into the harbor with currents. And there are analytical formulations to give you the max speed of these currents that you may expect. It is significant because as you have amplification of the oscillations, the displacement of water is significant. Now, as I said, let's try to generate a figure like this. It is a bit of a fun. And what I did is to provide you with code in R. It should open a new window. Before looking at the code, let's look here. You have a link to R. And last time I dedicated some time to this, so I'm not going back to it. Here you can download and install on your PC. It is very easy. I mean, to install it is a matter of a couple of minutes. And if you want to learn to use it, of course, it is a bit longer. And what happens when you, a bit longer, but not much longer. What happens when you open R? You see that there is a window console, which is waiting for your input, like MATLAB. And so here we can make computations. We can use functions like square root. I'm not going into the details because last time I spent a full hour, more than a full hour on this. So you can make computations. What is the advantage of using an open software, a public domain software? The advantage is that it is very easy to get assistance. So if you want to get documentation, documents, guides for learning R, you just have to go on the website or you Google for it and you find a lot of things. And also the open source community is very active in providing assistance. And there are a lot of packages, a lot of codes that are already prepared for R. It is the same as MATLAB. Also, MATLAB has a lot of prepared codes. The advantage here is that I think that in terms of getting support, it's easier. When you use an open software, which is very popular, like R is amazingly popular, it is easier to find information and support. So, and also it allows you to make some nice graphics, as we will see. Now, let's look at the code that I prepared. And first of all, there is a definition of some variables here, and the code can be cut and paste from the web to R. So I made a copy with the right of the mouse, and I go to the R console and I make a paste, and I define the variables. Now, if I type WI, you see it's 0. If I type capital H, is 2. So the first instruction are just assignment of variables, okay? And I mentioned to you before that there are functions that are pre-prepared into R, and the function like sqrt, which is square root, these functions, you have to specify argument, like in this case, the argument of the square root is the number I have to compute the square root of, and the argument is to be given between round parentheses. These are the very basics. So I just wanted to let you know there are functions that are already pre-prepared, and therefore before getting into something complicated, before writing codes in R, it's better if you check what's already embedded into it. And the support can be found on the web, or there is the help like !sqrt. It opens a web page with the help. You see there is a description of these two functions, ABS, absolute value, and sqrt. Okay, now let's now take this first part of the code. Let's copy these instructions. I don't want to really go into the details of what this instruction mean now. We will have the second part of the lecture today where we have an exercise that we will develop, which I will try to inspect in detail. Let me just for now make a cut and paste. So I copied it and let me paste it. Okay, and you see here that there is a plot window on the right, which appeared. And this refers to the calm conditions. This is it's a cross section of our Harbour. So what we see on the screen along the vertical direction is indeed the vertical direction. And on the right, you see the wall of the Harbour. And the horizontal line is the sea level in calm conditions. Just let's have a very quick look at the instructions. Here, I defined a vector Wi. The vector Wi is a repetition of 0 83 times. And this is the level of the sea level in calm conditions. And then I say plot Wi, which is this vector, with a line type equal L, with the limit of the x-axis, horizontal axis 0, 90. You see that it is drawn from 0 to 90, and the limits of the vertical axis from -5 to 5. And then I make a vertical line. This instruction, AB line, is drawing a straight line with it's a vertical line, V equal 83. So at the abscissa of 83, I draw this vertical line. So title, calm conditions, very good. And then I have a fourth cycle, which in a way, first of all, a fourth cycle. So cycles, you know, are essential elements of a programming language. So here it's a cycle that is repeated 10 times. And the cycle is just provoking a delay because it takes date and time from the system. And then it says, while the current time minus the time that I retrieved just before is less than 0.1 seconds, I do nothing. Just keep doing nothing for 1 second in this case, okay? And of course, if I want to increase the delay, I just have to increase from 0.1 to 0.2. So this is drawing the line in calm conditions. Now let's look at the next step. It is repeated 83 times. Why 83? Because I want to draw a wave that is traveling from the left to the right, from 0 to 83, because I decided to put the wall at the abscissa of 83. And here, what I'm doing is I am building a new vector Wi. So I am overwriting the vector of the calm conditions, but I am overwriting it step by step, because you see that only the part of the vector that goes from 1 to I is overwritten. And I overwrite it with the formula of the wave that is depicted in here. Just 1 second, I go back to the formula. This one. It is the first one, equation 1. And of course, here I put some parameters. I'm sorry. Here I put some parameters. So is cos, you see the A, capital H divided by 2, cos 2 pi. And then there is a sequence from 1 to I. And the sequence from 1 to I is, I go back to the web page, is x divided by L, which is also here, divided by L. And then there is the second part is time. Time, I relate time to x by setting the velocity of propagation of the wave divided by the period. So it is what you can find here, even without going into the details, it is this one. And then I plot this wave, title incoming wave. There is still the line of the wall, and then there is still the pause of time, otherwise it runs too fast. So let's then copy from the beginning to here. Okay, copy, paste here. And then let's look at the graph. Okay, paste. So you see here, I don't understand why there is, we will see. The wave is traveling up to there. I don't understand why it was flashing. I think the reason is just that the PC is a bit slow, because my PC was not flashing. Okay, let's make it again. And in order to make it again, let's just try not to overlap the console with the, okay. I make it again with another paste. You see there is calm condition, and then there is the propagation with the, it is a bit flashing. I don't understand why. Okay, this is the way that is incoming. And then at this point, the reflection starts. So the next part of the code is to start the reflected wave. Let's have a look. And the reflected wave is all in all similar, but I have a second wave, WII, which has a similar formulation. I just have to elaborate it a little bit more, because it is easier to write a wave that goes from 1 to 83 rather than drawing a wave that from 83 comes back to 1. It is a little bit more complicated in terms of coding, but it is really anything, it is really all in all the same thing. Okay, let's see, copy and paste. Here I am expecting also the standing wave to appear. I clear the console and let's paste it. Calm conditions, and then there is the incoming wave, and let's see what happens when we get to the head. I don't understand why it's so flashy. Unfortunately, we don't see, we see only the final result. Let me check why. Let me check how we can change things. Don't understand why it is perfectly working anyway. I'm sorry that the animation is not really. Let's try to do one thing. Let's try to. Okay. I'm trying to repeat it, but by changing the pause time. It's fine. And then it's okay. Oh. Lines. Lines. Okay. Then there is a line, and then there is the date. Okay, and then there is the while. Okay, I want to change this instruction. Let me put it minus 0.01. Maybe it becomes too faster. Too fast. Let's see. Too fast, and in any case, it didn't improve. So anyway, this is. Let me just go now also to the last part. The last part is just continuing the standing wave. So let me copy everything here and let's put it here. Okay, now it's getting into it. Then it will be flashing, unfortunately. But maybe at the end, I am interested in the end of the cycle. Okay, and this is now continuing. Just 1 second, let's wait for the cycle. Okay, and this is the picture of the standing wave. You see the free end on the right, the fixed end on the left, and that's it. And you see it's given by the superimposition of the reflected and incoming wave. Okay, now here we don't see amplification. It is just a summation of two waves which lasts forever, doesn't amplify. We get a standing wave with twice the amplitude, but we don't get amplification. So why we don't get amplification here? Because here we are just superimposing, we are not describing energy. We are just superimposing an incident wave and a reflected wave. We are not describing the energy of the system. Actually, what happens to the energy of the system in such a situation? You see that the incoming wave and the reflected wave give a push, look at the stream right, to the through of the first through of the standing wave. And if you look at the first crest of the standing wave, again, the two waves, the incoming one and the reflected one, give a push to the crest of the standing wave. This means that if I describe the energy of the system, I would have the Harbour that is getting energy because as I can see here, there is a mass displacement which is given by the fact that the two waves, the incoming one and the reflected one, in a way, they superimpose each other. But the incoming wave is continuing to bring energy into the Harbour. Is continuing, and I'm not describing this here because, as I said, here I'm just putting the two waves one over the other, but I'm not describing the energy of the system. If I had to describe the energy of the system, I should take into account that the incoming wave is bringing energy, and this energy may conflict with the energy accumulated by the bay. So if I didn't have this coincidence of crest with the crest and through with the through, there would be a conflict, and therefore the incoming wave would contribute to softening the standing wave, to opposing to it. But if I have a situation like I see on the screen, and this depends on the geometry of the Harbour and the frequency of the Harbour, like the fundamental frequency that we saw in the video before, if I have this coincidence of frequencies, then there is amplification. And amplification, in principle, may last forever. On the other hand, it's clear that when you get a lot of movement, a lot of displacement of mass, the assumption of no friction, it's not tenable. It's not tenable, and therefore, there is a dissipation of energy at a certain point, which increases and increases. And when the dissipation of energy equates the energy that is coming from the ocean, you get a kind of stabilization. But still, the amplification factor may be of the order of 15 or 20, which means that even a small wave with a long period, so you may have a very small wave with a small amplitude, with a very long period. Why long? Because the most dangerous frequency is the first one, is the first frequency, the frequency that takes the whole length of the harbor. So you may have a long period wave with a small oscillation, then it generates a standing wave with the factor of amplification of 20. So you understand you understand why people are putting attention on it. Actually, unfortunately, I don't have a video of a flood into an harbor originated by a standing wave, but there are several other videos showing the effect of resonance on structures. And I want to show you one, which is very famous, and it's also on Wikipedia, and which is the collapse of a bridge in 1940. I think it was in the United States. Just 1 second, bridge. Okay, the Tacoma Narrow Bridge. So here is described in Wikipedia. You see, this is the opening day, the inauguration day, and they brought soldiers walking with the same pace over the bridge. And you see in the video what happened here, because they had a video of it. Just wait for the advertisement. This is
the fundamental job of an engineer is to compare loading conditions to strengths. If the loads exceed the strengths, you know you've got a problem.
This is a bit too long. I will move forward.
Floods, snow, rain, ice, earthquake.
Taking a long time. Let me just download the full of it. So there are also some smaller pieces of this video. Just 1 second, let's see. Like this. YouTube.
Long distances with only 2 tires.
Let's see, maybe that now it's working.
Reducing the amount of material required, and more importantly, the cost. Collapsed in dramatic fashion. In fact, this failure was so dramatic, there's a good chance a ribbon occurrence across the Puget Sound. Unfortunately, that analogy, Washington and the Kitsap Peninsula, had the material required, and more importantly, the cost. This advantage of being able to span long distances while minimizing material gives suspension bridges
This is a good game.
appearance. But that same line of material reduces the rigidity and stiffness of the structure. Where before bridges were generally stiff enough that gravity was the only load that needed to be considered, now a new force started to impact their designs, the wind. In July 1940, the Tacoma Narrows Bridge opened to traffic between Tacoma, Washington, and the Kitsap Peninsula. At the time, it was the 3rd longest suspension bridge in the world. Financing construction of the bridge was a major obstacle, which led the state to pursue an innovative design. Rather than the originally proposed trusses, the bridge used 2 narrow plate girders to stiffen the deck, giving the bridge its iconic steel ribbon appearance across the Puget Sound. Unfortunately, that analogy extended beyond its appearance. Even during construction, it was apparent that the bridge was too flexible, even under moderate winds. Construction workers gave it the nickname Galloping Girder. Only 4 months after it opened, the bridge collapsed in dramatic fashion. In fact, this failure was so dramatic, there's a good chance you've seen this video before.
It was just people walking on it. And let me just check.
With resonance, small periodic driving forces, like pushing someone in a swing, can add up to large oscillations over.
Just 1 second, I want to see, because it was very short. Very short, so let's see. This is 4 minutes.
As you can see, this bridge was exceptionally long and narrow, over half a mile long, only 39 feet wide. It lasted just 4 months. During construction, we see the steel girders, 8 feet tall, which were supposed to stiffen the bridge against bending. However, some up and down vibration was observed during the entire useful life of the bridge. Here's opening day. On November 7th, the bridge suddenly went into a twisting motion. The wind speed was a steady 42 miles per hour. This was enough to keep the bridge oscillating in one of its natural modes of vibration for the period of 5 seconds. A professor of engineering went out to see what had happened. He's coming back, walking with some difficulty along the nodal line, which is the center stripe of the roadway.
Amazing.
It's remarkable that the girders were this flexible. This is photographed at normal speed. However, a collapse was inevitable after a little more than an hour of this. The car had been abandoned earlier. No one was injured in the whole affair. However, a small dog in the car was frightened and was afraid to come out, and he perished along with the bridge.
Okay. This is a nice demonstration of what resonance can induce. I think, as I see it, because I didn't read the Wikipedia page, I think it may be a combination of wind forcing, and at the beginning, I think the problem was the soldiers. But probably it's a combination also, because I see that there is a lot of wind. And given that it took a long time, fortunately, to collapse, people left it. In fact, there were no victims. So, but because people left, I think that probably there might be some other kind of forcing that continued the resonance. Okay. So I think the last thing, but I talked about it last week. So you understand that what it is really mattering here is the estimation of the natural frequency of the harbor. And there is this formula that you can have a look on, because I discussed it already. This formula, which is called Marian formula, which basically computes the travel time of the wave to get to the head of the harbor and come back. And therefore, you see, for a closed basin, the formula takes this expression. It depends on the number of nodes because it depends on the frequency. And then you take twice the length of the harbor divided by the wave celerity. GD, where D is the depth of the harbor, is the wave celerity. And then you divide by the number of nodes. But this is for closed basins. For open basins, it's this one. This is the formula. It is for the fundamental mode, you just have to compute, given that you have a free end, an antinode at one end, and a node at the other end, you have to take 4L instead of 2L for the length of the bay, because you have to double the length of the harbor. Why? Because you have one free end, and it's not so the fundamental frequency is twice the length, and then you have to multiply by 2 because you have also the path to come back, the time taken to come back. So this is the Merriam formula, which is like a preliminary computation. This is valid for rectangular basins. There are all the assumptions listed in the web page. And please make an effort to remember how it works, because this may be a question at the exam. So I just wanted to dedicate some more time, because I think this is interesting indeed. And it is also a topic that it's not easy to be understood. You are a student, you have a good knowledge of waves, mechanics, and therefore it is relatively easier for you. But it is not easy to understand reflection, to understand how resonance works. And if you look at the references, because you find several references also on the web, the math is very complicated, because they made the attempt to describe it mathematically, describe the hydrodynamics mathematically. What I did here is something more conceptual. I didn't go into the details. I just tried to explain to you how it works. The fact that in general it's very complicated is the reason why I wanted to insist again. Indeed, I published this lecture 1 week ago, and if you look now in Google for Harbour oscillations, already the lecture comes at in one of the first links, which means that you don't find much. Okay. Do you have any question? So we also took the
no question, Prof.
Okay, very good. No question. Very good. Now, we also took the opportunity to open R. We will open it again during after the break. But let me now start to talk about beach protection. And so the next link. So first, why should we talk about beach protection? Because when there is an harbor, in the proximity of an harbor, we induce a perturbation of the equilibrium, the hydrodynamic equilibrium. I would say the geomorphodynamic equilibrium of the system. And the system is the coastal system. And very often, when the presence of an harbor determines a perturbation of the equilibrium of beaches, if there are beaches around, of course. So very often, the harbor construction and the harbor management is associated to the management of the beaches. And I want to give you an example. It is a narrative description, so there is not much math here. Let me give you an example of a situation where it is a link that is close to the end of the lecture, the Tweed Sand Bypassing Project in Australia. This project, infrastructure was put in place to bypass an harbor, bypass with sand and harbor. Why? Because, let me look for a picture. Because this is the picture that I wanted to get. Let me see. Okay, good. Look here. This is the system, the coastal system. And there is a river getting into the ocean, and there is an harbor here. So basically, they used this natural bay to build an harbor here. Of course, you see also there is it's protected, the harbor, with some gates. Of course, you need to navigate the river to get into the harbor, and therefore they already at the beginning they trained the river. They protected the river in order to make sure that there was enough depth into the river for ensuring navigation. At the beginning, these walls, these protection walls, were not as extended as they are now. This is a current situation. What happened is that by building these walls, they broke the movement of sand along the river. In the original situation, especially during violent storms, the sand moved from the south. I think this is south. I'm not really sure. Maybe that I am inverting the orientation of the compass, but the sand moved from the lower part of the picture towards the upper part and crossed the river, used to cross the river. The movement of sand occurs mainly during storms. This is an area that is exposed, is much exposed to storms. And during high storms, indeed, the energy brought by the oceans, by the waves, was enough to cross the river for the sand. So there was a natural flux of sand from, as I said, the lower part of the picture to the upper part. And then they built the wall. By building the wall, the sand, of course, could not cross anymore, but actually the sand continued to cross. And the sand crossed at the end of the wall. And then the moral of the story was that a bar formed like an accumulation of sand at the river mouth, and they couldn't navigate the river anymore, or they had frequent need for maintenance. And therefore they decided to make the walls longer. But you see what happened? You see that the sand in the lower part of the picture, let's say it's south, reached the end of the wall, and at the end of the wall, the sand continued. You see that this clear zone here is a flux of sand, continued to cross, even if with a different, of course, a different path with respect to the previous situation. And on the other side, they got erosion. You see here, there is not much sand, and erosion went also behind the corner, and you see that the beaches here, they are completely eroded. You see, this is the beach called Kira. It looks like it's completely eroded. So they recognized it was a mistake to make the walls longer because indeed the sand got trapped here. And still they had the problem of the bar. It was a little bit more towards offshore, but they still had this problem. And also the fact that the walls were so long basically redirected the little amount of sand that was still crossing in offshore and not towards the beaches. So what they did at the beginning, they just did a lot of dredging with mechanical systems and brought the sand here. And also they took mechanically. They made a huge intervention, a removal of sand with mechanical means, and brought the sand beyond the river. But then they realized that they needed a permanent infrastructure and built this sand bypass. What is a sand bypass? It's a pipe that is connected to a pump. The pump is getting water from the ocean, water plus sand. And through the pipe, the sand is then released on the other side of the river. And this is permanently operational, usually during the night, because they don't want to create some problems to tourism with turbidity. So usually they pump during the night, but they pump 365 days a year. And this is a nice demonstration of how river training and operation of harbors can provoke these disturbances. And it is, if you have some time, there is also a video which we will not watch entirely, which is interesting because indeed this project, it is interesting to see. And this is a bit commercial, but you see.
The project also has restored and maintains the natural 150-meter jetty on the south side of the river.
This is the pipe
that intercept the northward directed natural flow of sand before it reaches the river entrance. These pumps collect the sand, Once or twice per year, sand is delivered to Harbour Beach to mitigate erosion.
You see the
If
pipe
required,
that is.
the system can also deliver sand to Rainbow Bay, Greenmount, and Kira. Once delivered, the sand is transported by waves and currents to nourish the southern Gold Coast beaches. Whilst the jetty does a fantastic job at collecting most of the sand, regular dredging with a dredge vessel is required to collect sand that was not intercepted. The dredge vessel removes sand across the Tweed River entrance area and delivers it to approved nearby offshore locations, commercial and recreational uses, surrounding beaches. This means locals and tourists get to enjoy that. Maintaining coastal sand,
Okay.
favorable outcomes to the coastal environment. Tweed Sand Bypassing undertakes frequent monitoring activity.
They are keeping the system monitored. They have biological indicators to make sure that, you know, this release, concentrated releases of sand can induce turbidity and can have an environmental impact. But they are monitoring carefully. Okay, so this is why we focus also on beach protection, because it is frequently needed in the vicinity of harbors. Okay, now, first of all, keep in mind that beaches are a very active environment, a very dynamic environment, and they are the subject of ongoing research because it's not easy to describe their morphodynamics. It's not easy to describe erosion and accretion, which may alternate each other. Typically during the winter season, you have prevalent erosion, and during summer, there is prevalent accretion. So it is really a very dynamical system. It is studied by the discipline of beach hydrodynamics and morphodynamics. As I said, I'm focusing on it in the lectures of coastal engineering. So we will not go into details here. But I am interested in trying to classify the interventions because these very often require some engineering design. And I don't have a PowerPoint, so I am increasing the font and I'm trying to use the screen just as a guidance for me. So there are several categories of interventions that we can use in order to better remember what are the possible solutions. First of all, we don't have to exclude the managed retreat, which means that in the presence of coastal erosion, we may also decide to retreat from the beach, or at least I'm not saying that we may decide to close the beach. Okay, this could be a solution, but a possible solution could be also to manage a retreat, because erosion doesn't last forever. And basically the system reacts to erosion by the natural system by ensuring that there is a compensation. And therefore, in the presence of a perturbation, the system may react by reaching a new equilibrium. And this new equilibrium, it is in the presence of erosion, is found at the expense of accepting some erosion. So if there is room to retreat, this may be a possibility. Retreat means that if you have a beach that is eroded, once that erosion caused the formation of a bay, the bay is more protected, and then erosion may stop. So in some conditions, indeed, the retreat, to manage a retreat, if you have room, unfortunately, in the Western world, it's difficult to have room because usually we have urbanized the area just behind the beaches. But if one has room, it can be a possibility. Of course, what we have to find is to identify a new line of defense and to study the system and identify what could be a new equilibrium. But this is something that we don't have to exclude a priori. And then the counterpart of a managed retreat is an intervention that aims to hold the line. And the classical example is the seawall. The seawall is an hard intervention, what is called also a gray or black infrastructure, which means that you established in a way a constraint. You build a constraint, which is an hard constraint. And of course, this means, first of all, an environmental impact, and means that you are losing the beach unless you couple the seawall with beach protections, which anyway, for their impact on tourism, are not really the best solution. And then there are interventions that aim to move the shoreline forward in the seaward direction. And then there are indirect measures, how to move the shoreline forward, for instance, through beach replenishment or by making a sand bypass, or by building structure like breakwaters that protect the beach from erosion and favor their creation. There are also indirect measurements like favoring the green solutions, favoring the growth of the vegetation, or anyway, these indirect measurements don't modify the hydrodynamics of the beach, but usually they aim to make the beach more resistant with respect to erosion. These are methods that are very popular nowadays. They are called also green engineering methods, nature-based solutions. Of course, they are very appealing, and you understand why, because they are appealing because they are restoring a kind of natural environment, and they are reversible solutions. So indeed, these are interesting options. The problem is their effectiveness. These are solutions that usually are not effective at the very local level. They need to be very widespread, they need to be applied at a very large spatial scale. And they are difficult to design, they are difficult to model, because nature by definition is not something that you can model precisely. It's not like a structure. If you build a seawall, it's a clear case where a model is very simple. And to model it, to design it is very simple. To describe the dynamics of these natural solutions, it's not easy. So there is also a technical problem. And there is also the problem of their strength, which is not very high. They are weak in a way. They are weak solutions because they are natural, and therefore the equilibrium of nature is always a bit delicate. So, for instance, if you stimulate the growth of vegetation and you get a storm with a lot of salt water invading the vegetated area, everything is destroyed for a bit of a time. So they are appealing solutions, but often they may be not enough. There is also one more thing to say. The green solutions, while they are appealing on the one hand for the people that are not directly threatened by erosion, by the sea, they are not appealing at all for people who feel threatened by a flood, by a storm surge, by an hurricane. And so communication also is a bit delicate. This is not a technical problem, but still it's a management problem. There is another classification which we may use between active measures, which modify the local hydrodynamic behaviors, and passive measures, protect the coast from erosion without modifying the hydrodynamic circulation. I just made the example of the nature-based solutions. So active measures include breakwaters, groins, beach nourishment, and sand bypass. Passive measures include seawall, revetments, berm protections. Okay, I propose to make the break now, and then we get back to this discussion in the next couple of hours. I am leaving the video open. Sorry, I am leaving the registration open, but I am turning camera and mic off like I did the last time. Okay, here we are.
Okay, Prof. Yes.
Thank you. Thank you very much. Giorgio, I take this opportunity to ask you, did you attend coastal engineering? Do you have it in your study plan, the course that I am teaching in the first semester?
Yes, yes, we have done. With
Okay.
Archetti.
Okay, good. With Archetti, but you attended also my lectures?
Yes, yes, and Brat.
Yeah, yeah, perfect. Thanks. Okay.
And
So,
sorry, I approfitto, ma the exam with you and Professor Brat could be done
whenever you want. It's
okay.
It's no problem because I scheduled several exams in February, but if you want to take it also now during these weeks, it's not a problem.
Okay, perfect. Perfect.
I will make it myself. I am joining the part of Professor Brat and my part. So you will take the exam with me, only with me.
Okay, okay, perfect.
Yeah.
I will let you know if.
Yeah, thanks a lot.
Okay, thank you.
So let's move forward a little bit with the coastal protections. I think you already know everything about breakwater, groins, beach nourishment, but let me just explore with you these links. So breakwaters are protections that are parallel to the coastline. So their direction is along shore. And of course, their purpose, I think you know better than me, their purpose is to contribute to decrease the energy of waves before reaching the beach. Because given that you attended already my lectures of coastal engineering, you know that the capacity of waves to erode a beach is directly proportional to the energy of the wave. This is what we usually assume. And therefore, in order to limit the erosion, we have to decrease the energy of waves. So the purpose of breakwater is indeed reducing the energy of waves. As I said, they are displaced along shore direction. So let's now look at groins. Groins are perpendicular to breakwaters, and therefore they are displaced in the across shore direction. And they are, in a way, complementary to breakwaters, because the purpose of a breakwater, besides by reducing the energy of the wave, is that of mitigating the sediment transport across shore. The purpose of groins is to reduce the sediment transport along shore. So they may be coupled. We will see how groins can be designed with a specific lecture, so I'm not going into the details now. In a way, these measures are complementary. Keep in mind that groin can be spelled with the Y or with the I. So it depends on the US English is with the I, and the UK English is with the Y. The pronunciation is the same, and just they are synonyms. In my lectures, you will find sometimes the I, sometimes the Y. Okay. And then there is beach nourishment, also called beach replenishment. So one example is sand bypassing. You see here there is a device that is bringing sand from a location and bringing sand here to replenish the beach. And here there is another picture of a beach that has been subjected to a nourishment project. Okay. And these are active measures and also sand bypass, which is a kind of beach nourishment. And then we have the passive measures, seawalls and revetments. What are revetments? Let's see, this is a seawall here. This is a seawall, it's a modern seawall. And this is a seawall. So here, let's say revetment, I don't think there are pictures here. So let's just see beach that we understand each other's revetments here, images. Okay, this is an example of a revetment, like here in the coastal Vicky revetment. Let's see if yeah, you see here this picture. It's a kind of protection that is made over the beach. The revetment may be also composed by using cobbles, like you see here. So the revetment may be composed by fixed paving or semi-fixed, like in this picture, or by cobbles. Cobbles usually are called by their name. So we say beach protection with cobbles. But for instance, here, this is also a revetment. And you see that, okay, these are not really cobbles, but if you see here, this is also, 1 second. Here you see a series of revetments. You see here, these are cobbles, basically. Okay. And then we have also berm protections. You know that the berm is the part of the beach which is located at the end of the wave run-up, at the end of the swash zone. So at the last end of the average wave. So the wave climbs up along the beach in the across shore direction to a certain extent. At the limit of the wave run-up along across the beach, there is a deposition of sediments. This deposition of sediments originates the berm, and we talked about it in coastal engineering. And the berm is a kind of natural protection. Let's see some images to make sure that we understand each other. I am sure that we understand each other, but let's see images here. So let's see a typical berm. I think this is a nice sketch. Let's see if we can open this. Anyway, here there is a nice figure of a berm. So the berm is located around here, you see, and usually you see litters because it's the deposition operated by waves. And you see that it's like a step. It's like a step. And it is a nice figure because it shows that the berm, first of all, it's a natural defense because it's more coherent, so it's more resilient towards erosion. And you see, even with a so small elevation, you can see some growth of vegetation, and the vegetation contributes to keeping, to solidify the berm, to give cohesion to the berm. And this is something that usually is the berm is located at the end of the summer waves. It's not located at the end of the storm waves. At the end of the storm waves, you have another step, which is the dune. The dune is higher than the berm, much higher. And much higher, I mean, maybe the dune may be also 6-7 meters high. The berm is half a meter. Between the berm and the dune, you may have a small channel, which is called the runnel. Over the dune, in view of its height, there is more fresh water and then more vegetation. You see that behind the berm, you have trees. Typically, indeed, over the dune, we can find trees. These structures, berm and dune, they are protections. And therefore, one possibility to increase the resilience of the beach against erosion is to protect the berm. And I just want to mention that on the Adriatic Sea, on the Adriatic Sea, if you go on the commercial beaches, you don't see neither the dune nor the berm, because I mean the berm, as you see, it is there are floating material. I couldn't find the word. There is floating material that was transported by the waves that is left there. Even if it's not plastic, still they may be pieces of woods, they may be some cobbles, and so the berm is not very nice to see for the tourism. You know, for the tourism, especially on the Adriatic Sea, they tend to make the beach perfect. So every night they basically smooth it with the mechanic material, and with this way of operating beaches, of course, removes any obstacle to tourism like berm and dune. So you can't find them. But if you go in free beaches, even on the Adriatic Sea, you see very nice examples of berms and dunes. As I said, the berm is usually located at the end of the summer waves. The dune is located at the end of the storm waves. And as I said, a typical protection for beaches on the Adriatic Sea for commercial purposes is called beach scrapping. It means that you take all the sand from the seaside and you bring it back to the berm position, because you don't want that sand left there, because during the winter you may have storms and therefore erosion. So one possibility is to get the sand, bring it back, to retreat it at the level of the berm. And in a way, in doing so, they reconstruct a previous dune that was there, but was in a way flattened down in order to use the beach for commercial purposes. Beach scrapping is very diffused. If you go during these weeks on the beaches of the Adriatic Sea, you will probably find people that are bringing back the sand, preparing for Easter, bringing back the sand to the summer position. This kind of management of beaches, on the one hand, is very smart, because of course you don't want the sand to be eroded away and you bring it back. On the other hand, it destroys any form of ecosystem that still survives in the body of a beach. Even in the presence of salt water, there is a microfauna. There are several living species that are hosted by a beach, even when you don't see any vegetation. And unfortunately, this management, from a biological point of view, it's not very biocompatible, let's say. Okay, so as I said, berm protection is a possibility, and there are several ways to make a berm protection. Now, let's get a schematic of direct measures, and these schematics are very nice. I borrowed it from a colleague who is teaching here home, and I think they are very nice because they show different solutions that we can adopt in terms of submerged structures, emerging structures, and combination thereof. So first of all, seawalls, there is not much to say. In these figures, look at the legend here. There is the original coastline, which is marked by a black line, black straight line. The emerging structures are marked with crossing lines. Dashed line identifies submerged structures. The emerging structures are marked with the crossing lines and have a continuous black line marking their contour. And then the protected breaks. What are the protected breaks? They are breaks that are maybe breaks in the structures that may be protected, meaning that when you have a break into a structure, like a break in a breakwater, you have a concentration of currents along the break, across the break. And this may cause erosion. So you may want to protect these breaks in terms of avoiding that there is a concentration of erosion on the sea bottom. Okay. So, and then with the black circle, we identify here emerging signals. So for the seawards, there is not much to say. They are emerging, typically, emerging structures. And in this case, in the second figure, you see breakwater with protected breaks. The breakwater is, in this case, emerging. And these are the structures that are contoured by the black thick line. And then you see that we have submerged protections, which may be realized by building a submerged breakwater, for instance, by putting boulders in the bottom of the sea. And these are submerged protections to protect the breaks. Because if you don't protect the breaks and you have a concentration of erosion there, then it may cause a failure of the breakwater structure. Breakwaters can be submerged. Usually when we submerge them, and this is the third figure, this one, when we submerge them, we may mark them with signals for the both, of course. And here we have also partially submerged, we have protected breaks and partially submerged groins. So the breakwaters can be coupled with groins. In particular, groins may be used, may be efficiently coupled with breakwaters when the breakwaters are submerged, because otherwise, you know, if you contour a beach with a breakwater and two groins, it's like closing it. So also in terms of hydrodynamics for preserving the water quality, in terms of visual appearance, is not very advisable. So sometimes you can find them coupled, but maybe that we could consider submerged structures. The breakwater, the groins usually are not submerged, usually, even if in principle it is possible to consider to submerge them, at least in part. The groins can be distinguished in two types, the T-groins and the straight groins. The T-groins are more effective in trapping the long-shore sediment transport, of course, because you have the formation of a pocket in correspondence of the T, of the head of the groin. We can use small highlands, and we can use replenishments, as we said. Replenishment is an interesting option. I will talk about it at the end of the discussion of these sketches. So now, replenishment may be coupled with groins and breakwaters, so we may have an integration of measures. Usually, this is advisable because if you just replenish a beach, you have to expect that there is a subsequent erosion. And the subsequent erosion may be quite fast because if you feed the process of erosion with sand, the process accelerates. I mean, to bring sand in a place where which is susceptible to erosion means accelerating the process. So maybe that we can compensate with groins or breakwaters, depending on the dominant direction of the sediment transport. We can also combine the groins with submerged breakwater. A submerged breakwater is similar to a bar, or with emerging breakwater with signals. And here we have a replenishment with groins and T-groins. Okay, now let's talk about beach replenishment, because it is an interesting option. But on the one hand, as I just said, we may need to couple the replenishment with some structural intervention. And second, there is an important choice to be made about the size of the sand. In fact, especially in the past, it was considered a good practice to use a sand with the larger diameter of the grains with respect to the original sand. First, keep in mind that it's not easy to find a sand that is similar to the original. Okay, if you take it from the vicinity, it's okay, but with a bypass, it may be possible. On the other hand, of course, if you have erosion, you don't have sand. And then if you get a sand close by, it may be different because the size of the sand is dictated by very local conditions. So it is determined by the inflow of sand from rivers. And it is also determined by the hydrodynamics of the beach. So it is a very local feature. And therefore, it is indeed, it is not easy to find a sand that is precisely looking as the original one and is physically identical. It's almost impossible. So the recommendation, especially in the past, was to bring a sand with a larger grain size, and of course, because it is more resistant to erosion. On the other hand, we noticed that using a larger grain size makes the replenishment very evident, very visible. So it is not good looking. And also in terms of the biophysical equilibrium of the beach, it may not be the solution that is most indicated because, of course, if the original grain size was different, there is a reason. And this reason is not only related to physical features, also biological features. And therefore, now the suggestion is, okay, maybe a little bit larger, but to try to keep unaltered the original configuration of the beach. In any case, you have to consider that replenishment, especially if it's not associated to structural protections, it's a temporary solution. And probably it needs to be repeated regularly, needs to be scheduled with a regular periodicity. But indeed, it is something that it's frequently considered. Okay, I think I would prefer that I stop now with this lecture, and I take it back next Wednesday. We are close to the conclusion, but still there is something more. There are some more figures and pictures that I wanted to show you. So I prefer now that we concentrate on the exercise because we have less than 1 hour and the exercise is interesting, I think, at least in my intention. Okay, so I still have my R window open. Let me clear the screen and let me go to. Sorry,
how do you clear the environment
in R? Okay, there is first there is a possibility. I show you, because we created some, we defined some variables vector, and you can see what you created. They clear the screen, you mean?
No, clear the variables.
Okay, perfect. Here are the variables that we defined. Now, to clear them, what you can do is first to go out from R with this function, and then it asks you, do you want to save? If you say no, it's cleared up. Okay, this is a possibility. Now, I don't know if there is a function to remove everything, because you can remove variables with the rm function. I think, but you need to specify the name of the variable. Okay, D50M. Let me just see rm, because I think we can use remove to remove everything. Let's see. remove the objects to be removed. Let's see. Lotran, remove almost everything in the working environment. You will get no warning, so don't use this unless you are really sure. And it is this one. So let's do it. I have nothing to lose here, so it's not a problem. Okay, and yes. Yeah, everything was removed. Because it's, I think it is probably, I could do like this. Oh, okay, list. This is the command. Because it takes a list of objects from ls. ls was the command that I used here to get the overall list. And there is no warning, so you have to be careful. There is indeed in R, and I think also in MATLAB, there is no possibility to undo anything. So it is better if you save once in a while, and you can save with save image. Just 1 second. So save that image. Save that image saves the workspace. Or save history saves the history, which is the list of the previous commands. Because you see that if I go back with arrow up, I get the list of the previous commands. I think in R it's similar. Okay. Anyway, now we cleared the workspace. Okay, good. So let's go back to here. And let's get the exercise, computation of wind actions on a moored ship and computation of mooring forces. So before I read it, let me just make an exercise into R. And let's write a function, because this is a big step forward. So there are, you can make a program into R simply by making a cut and paste as I did before. But you can also make a program into R by writing a function. The functions, we know what they are. And because we used, for instance, sqrt. Now, let's write a function that makes the sum of two numbers. And this function takes as argument the two numbers that I have to sum and gives back their sum. Okay, so let's define it in this way. We need to decide the name, like sum to number. Sum to number, it's equal function. And then I have to give the argument A, B. And then if I press enter, you see that there is a plus, because the plus means that R is waiting for the content of the function. Now, for now, I just told it that the function has two arguments. Okay, given that the function contains more than one instruction, I need to open a curly bracket. The curly bracket, it depends on your keyboard. Usually I get it by pressing Alt-GR, which is placed on the right of the space bar. And while I keep pressed Alt-GR, I press the number 7. This is a possibility. Otherwise, you may have directly the curly bracket in your keyboard, like here. I have, let me see, I think, okay. And then if I put a curly bracket, R understands that there are several sequences of commands several commands to be executed. Okay, now I can write C is equal to A plus B. And then I press return, and it's still waiting because the curly bracket is still open. Now I can just give the instruction to return on the screen C. And then I can close my curly bracket. Now, nothing happens. But if I look at ls at the list now, I see the function. And if I wanted to see the content of the function without applying it, I just need to write the name. And this works for any function. If I type sqrt, there is the display of the content, which is something that we don't understand because it's calling an internal routine. Okay, and now let me clear the screen. If I make sum two numbers, number A equal 3, B equal 4, I get 7. It is not necessary that I give the name of the arguments. 7. One thing that I could do, let me just rewrite the function, okay? One thing that I could do, sorry. I could write something like this. I could give default to A and B. Let's compute the sum. I just wanted, because in the exercise, actually, we develop it by using a function and return C. Good. And then if I make sum two numbers and the two number, I get, and I open and close the parentheses, I get the sum of the two default values. Okay, and then we learned how to write a function. Perfect. Now we can remove it. Clear the screen, and let's go to our exercise. So there is a ship, which you can see here, the sketch, with the location of the pivot point. The pivot point is the location of the point where the ship naturally rotates around, okay, which is basically it's very close or coincident with the center of gravity of the submerged part of the ship. If you get the ship exposed to wind, the wind is applied, the resulting force of the wind is applied in the center of gravity of the windage area, which is the outside part of the ship. And therefore, usually the center of gravity of the windage area doesn't match with the pivot point. So when you get wind, the result is a drift and a rotation, because the ship tends to rotate around the pivot point, and the resulting force of the wind is applied not on the same vertical with respect to the pivot point, and therefore you get as a result a drift and a rotation. You get as a result, a resulting force causing the drift and a rotating moment. So what we usually do in order to summarize the action of wind is to apply the resulting force on the pivot point and to apply a momentum which causes a rotation on the around the vertical line passing from the pivot point. Is it clear? Okay, good. So you have this ship, it is moored, and it is moored, and we have a wind that is acting along the y direction. So it's a wind that brings the ship out of the berth, tend to bring the ship out of the berth. And we have these spring lines. These spring lines, actually, I consider only the red ones here in order to simplify the problem. The yellow one plus the red one, spring lines, identify what is a typical configuration of a mooring system for a ship like this. If you remove the yellow one, you understand that there is less safety against a movement along the longitudinal direction, along the X direction here. But let's simplify it. So let's. I don't remember if I kept only the yellow one, or let me see. Let's see. Within direction. Mooring line composed by 3 rope of cross-section. The elastic model. I think I kept only the red ones. Yeah, because you see that there are acronyms only in the mooring points, in the bollards of the red lines. Of course, the procedure doesn't change if you put additional lines, but you know, as you will see, it's not an easy procedure. Okay, so we have some forcing, and so let's read it. So there is the displacement, the tonnage of the boat. I don't think it is used here. Waterline length of 117 meters. Remember how we define the waterline length. A draft or draught of 5 meters, a beam of 12 meters, pivot point located at 55 meters from stern, which means this is stern, okay, and side projected wind area of 905 square 50 square meters. Okay, and we have 6 mooring lines, red lines. The yellow lines are additional ones that are shown for the sake of illustrating further possible lines. The ship is subjected to an extreme wind velocity of 50 knots, about 90 kilometers per hour. It's quite a huge, with wind direction perpendicular to the ship's center line. So the wind direction is along the y-axis, just to simplify it, okay? The ship is moored with mooring lines composed by 3 ropes. So each mooring line is composed by 3 ropes, which are intertwined each other. I don't know how to say in English, but they are in a way, okay, composed. Cross-sectional area of each rope is 30 square centimeter, and the elastic modulus of each rope is 125 kilonewton per square centimeter, and the breaking tension is 25 kilonewton per square centimeter. It is important, the elastic modulus, because the mooring lines are not rigid lines. We want elastic lines, indeed. They don't have a huge elasticity, but we want some elasticity for obvious reasons, because of a greater resilience. But the fact that they are elastic lines, you understand the computation is not so easy, because you have an elastic body to deal with. Now we have to compute first the wind force and the yaw moment, and the mooring forces and safety factors. Okay, now we have the coordinates of B and C. What are B and C? Let's look here. B is the coordinate of the bollards, and C is the coordinate of the chocks. The chocks are, I think you know what they are, but let me just, I have a picture here of a chock. 1 second. I'm quite sure. See here to see a picture of a chock. So these are the, sorry. These are, where is my mouse? This is the chock. These are the bits. There is written here, mooring chocks. These are the mooring bits. And on the bird side, the spring lines are connected to the bollards. So we have the coordinates of, just a second, of bollards and chocks here. Now, to make the computation, we assume that the mooring lines are horizontal. Usually they are inclined, but let's assume that they are horizontal. It's not a huge complication if they are inclined, but let's take them horizontal. And CW is the coefficient, is the wind coefficient. Let's assume it 1.3. And mooring lines are 50% longer from bit to bollards than the distance between bollard and chocks. This means that I have the coordinates of Bollard and chocks. In order to identify the full length of the spring line, I have to increase the distance between Bollard and chocks 15%. Okay, and we want that the safety factors are greater than 10. Good. Now, first of all, mooring lines. Let's read these indications, which are interesting, I think, because this is an exercise actually, but there is a lot of information that is also included here. So the least possible number of mooring lines shall be adopted to simplify mooring maneuvers and tensioning. So the lower the number of the mooring lines, the better. The mooring lines and the fenders should be symmetrically distributed with respect to the center of the ship. The objective is to distribute the loads homogeneously among all the mooring and fenders and reduce the coupling between different movements. Okay, the mooring lines shall be displaced as horizontally as possible. Okay, to reduce, of course, if it is much inclined, there is an amplification of the force, because what matters is the horizontal component in this case. And therefore, if you have a vertical mooring line, it doesn't offer any resistance to, as we know, to the horizontal components. And what is the max inclination? As you see here, 25-30 degrees. Keep in mind that the inclination of the mooring lines depends on the load of the ship and also on the water level of the sea, which may be changing in some conditions quite significantly. The mooring lines shall be aligned as much as possible with the direction of the movement they want to avoid, okay? They want to restrict. For longitudinal mooring and continuous berthing lines, the optimum setting of the springs of the mooring lines should be head, stern, and breast lines drawn from the ship as close to bow and stern as possible, together with springs connected to the ship at bow and stern at distances equivalent to 1/4 of the length. Let's see here. And this is the stern mooring lines. This is the bow mooring line, and these are spring mooring lines. Let me see if I use the bow and stern lines. Okay. Breast lines, B1 and B6. Sorry, these are breast lines. I forgot to say this. And at stern and breast. Okay. Springs connected to the ship at bow and stern at distances of 1/4. These are the springs at distance of 1/4. Okay, I think I had a box which I presented to you in one of the previous lectures on the naming of the mooring lines, just to refresh your memory. And I think it was in the lecture dedicated to port planning and environmental impact. Okay, the bow and stern lines should be laid out forming 45 degrees. So if you look here, about 45 degrees here and here. Okay, and the breast lines. The breast lines should B1 and B6 shall be perpendicular to the longitudinal axis of the ship. And for large ship, spring-lined application can occur, located symmetrically, okay. And this is the application. You see, these are spring lines which are duplicated. And then the mooring line of the same function, breast line, bow, or stern lines, or spring lines, should be of the same material and of equal length in order to maintain symmetry of the load. Same material means same elasticity. Equal length means same elongation after forcing. Mooring lines should preferably be long and few and made of a material with high deformation capacity, what we said just a few minutes ago, to transmit lower loads. When significant movements are to be avoided, galvanized steel lines may be a more appropriate solution, galvanized to avoid corrosion. The optimal length varies from 35 to 50 meters, according to the type of ship, of course. And lengths of less than 30 meters should be avoided because they have reduced elasticity. And the number of the optimum separation between fender axes should be less than or equal to 0.15 L. Okay, where L is the shortest length among the design ship for continuous berth fronts. Okay, these solutions, these indications, you don't have to remember them by memory for the exam. Just maybe the terminology of the spring lines, bow, stern, spring, breast, etc. Now, the solution, we got to the computation of the wind force into R. It's quite easy. We can do this, we can repeat it into R. So, and we can define CW equal 1.3. 1 second, I wanted to keep the two windows open on the screen together. Good. And then AW is 950, I think. AW 950. And then the sin phi, I think phi is 90 degrees, so the sin is 1 and the cos is 0, correct? Yes. So I would say that we can avoid to the definition of the angle. Gamma W is 0.01225. And the wind velocity is 92.6, just 1 second. Okay, 92.6, we can make VW equal 92.6. And I think I don't need anything more. So let's try to make the computation. PW is equal to GW times AW, because the sin is 1, times gamma W times VW squared divided by 2 divided by 9.81. Let's see the result. It will be for sure wrong. Yeah. So let's see why. Because actually, it should be like this. And actually, I think it should be correct. Let's see. W950 0.01225. Yeah. And no, sorry. The Y2572. Yeah, because the wind velocity it was in kilometers per hour. So VW, I need to it is let's see, 2572. Okay, 25.72. Good. And now I can repeat the computation. And now let's see. Okay, now it's correct. So the wind velocity is quite easy. Now let's compute the rotational moment. It's let's read what's written here. First of all, remember the wind force is applied to the center of gravity of the windage area. So the rotational moment results from the wind force be applied to the center of gravity of the windage area, which is shifted with respect to the pivot point. Then we can compute in a simplified way, but this is suggested by this reference here, which you can download. we can compute the rotational moment in a simplified way by the product of PW, the length waterline, and a coefficient, which is given into a graphical abacus. The coefficient is C, capital C, XYW. And here you can see an abacus that, depending on the angle of approach of wind to the ship, in our case is 90 degrees, it gives the suggested value for CXYW, which is in this case minus 0.04. Therefore, I can compute here MW as let's see, let's forget the minus 0.04 times there is a CPW times 117, which is the length of the line, or what length of the water line. MW, I think it's okay. So this is anti-clockwise, I would say, because it's clockwise if I put the minus. And in any case, let's see the figure here. So I think the ship should rotate anti-clockwise because the center of gravity of the windage area is shifted on the right with respect to the pivot point. I say that is shifted on the right because I remember that the pivot point is displaced at 55 meters from stern, which means that given that the ship is 117 meters long, if I measure 55 from the stern, I get more or less here. So the wind is blowing along this direction, so the rotation is anti-clockwise. So this is consistent with the fact that here I got a negative clockwise. Okay, and it's always important that you get a perception of your problem, of what happens, an intuition of what will happen. This is extremely important. Okay, now there is the computation of the mooring forces. I want to explain to you the procedure, and then we go to the computation. Now, the procedure is a bit complicated, and it's a procedure that decomposes a driving force, a drift force, and a rotational moment into forces acting along the mooring lines. So the forces, the wind force and the rotational moment are applied to a rigid body. And the rigid body is connected to the berth through elastic mooring lines with their direction. We made several simplifying assumptions, horizontal mooring lines, etc., and the mooring lines with the same section. But still, this is a structural mechanics problem, which you may have learned how to deal with because structural mechanics is the composition of forcings. So it is something that in principle we know how to manage. But the fact that the constraints are elastic mooring lines, it makes the problem an elastic problem. So it is really not the simplest computation that we can make. I give to you here the reference of the procedure. So here we refer to the computation method proposed by the Department of the Naval Sea System Command. And let's see, there is a PDF which you can look at. It's not easy to read these references. because they make an heavy use of math. Okay, but the computation that I'm proposing to you, the details are reported here. I simplified the solution presented by this PDF. And calculation, first of all, let's recap the assumptions. The elastic modulus of the mooring line does not vary with mooring forces. Okay, it's a constant. Mooring line arrangement is symmetrical with respect to the y-axis. And if you see the sketch here, it's symmetrical. Okay, if you look at the red lines. Okay. Yaw moment, MV, and lateral force Py are applied to the ship pivot point because, of course, we computed the forcing, the wind forcing. If we want now to compute the mooring forces, we have to apply this resulting wind force to the pivot point of the ship. And then, of course, we have to add the rotational moment. The mooring lines are assumed to run horizontally. Very good. But in the reference that I'm providing to you, there are instructions to relax the assumptions, this assumption. And let's now look at the step-by-step procedure. Until about 2/3 of it is very straightforward. And then the final computation, which is the actual decomposition of the wind force and the yaw moment along the mooring lines, we don't get into details. It's a pure procedure of structural mechanics. So maybe that you have already some knowledge of it. Otherwise, my suggestion is to take it for granted and just trust that it's a procedure of structural mechanics. Now, let's read the steps, because the first, as I said, are straightforward. So we need to take the coordinates of bits, chocks and bollards. Actually, here we have only bollards and chocks, which is fine because we can assume that the spring lines have their end point in the chocks, but I have to consider their longer extension, 50%, 15%. Determine horizontal length of each mooring line from bits to bollards. Okay. Determine total cross-sectional area of each mooring line, which is the product of the rope cross-section times the number of parts, the number of ropes per mooring lines, normally 3, and here we have 3. Determine the elastic modulus for each mooring line from producer. This is an input information. Determine the angle phi between each mooring line and the y-axis. And this is why we work only with the coordinates of bollard and chocks, because these coordinates are determining this angle phi. Determine the length of the mooring line between the chocks and mooring bits, as well as the length between the chock and the bollard. Okay. Determine total braking strength for each mooring line. Let's call it BS. It is needed for computing the safety factor. Determine the spring constant for each mooring line, which is given by the product of Ki. Oh, sorry, it's the spring constant is Ki, which is given by the product of the elastic modulus divided by AI and Li. Li is the length of the mooring line, and Li, okay, and AI is the cross section, if I well remember. Let's see. Yeah, is the cross section. So we have to compute the simple product for each mooring line. Now we have to determine the so-called spring component in the spring component in the y direction, which is the product of Ki times the cosine of the angle of the mooring line. This is also straightforward. Now we have to determine the product, and here it becomes a little bit obscure now, the product of the computed Kyi times capital Xi, where capital Xi is the coordinate is the x coordinate of choke I. And this is the start of the decomposition. And then we have to determine this product, Kyi times the square of Xi. And then we have to compute these summations A and B and C for each mooring line. And then we have to apply the total external lateral force P and yaw moment M to the ship pivot point. This is fine. And then with this formula, we compute the ship's movement in the y direction. We have a movement because these are elastic lines. And the ship movement in the y direction is called sigma y, which is given by this relationship here. And we don't get into details. XPP is the x coordinate of the pivot point. In our case, XPP is 0. Now we have to compute the rotation of the ship around the vertical axis. The formula is here. It uses the quantity A, B, and C that we computed before. Now we are ready for each line to calculate its force component, which is directed along the direction of the mooring line, and it is given by this product. Sorry, it is given along the y direction. In the direction of the mooring line is the next step. Determine the safety factor. This is easy. PS divided by TI. And at the end of the story, you may check that the sum of the y components along each mooring line is equal to Py, which is the wind force, the drift component of the wind force. That's it. You don't have to remember this for the exam, of course. Now we can pass to the R code. We may move forward into R like we started, step by step, but I think we are ready now to write a function, to resolve this problem through a function, because I think it is an interesting exercise. So the function, basically, it is useful if we had to repeat the same computation with different input information, like wind, velocity, which changes, etc. So let's have a look at the code. Sorry. Okay. I am opening it with the notepad. And here I have the first instructions into R, which the first two lines just define the coordinates of coordinates bollard and coordinates chocks. So let's copy and paste them. This is the definition of a matrix. C-bind means columns bind. And you see that this is a matrix with the coordinates. And therefore, I am putting into a matrix two columns with the X and Y coordinates. Good. Now, here there is the function. 1 second. Okay. I don't know where this was saved, this file. I just want to take a quick approach to it. And now this function, which is built here, you see that there is a definition of a function here with default values for the parameters, for the arguments. I could copy and paste each line into R. I could even select everything and paste it into R. In this way, the function would be automatically loaded. Another possibility, which I recommend, is to source the whole file. But I have to find it, so I think it may be somewhere in download. Let's see. I think the easiest way to find the file is to use a file manager. No, it's not. Sorry, it's not here. Okay, here it is. Download, I think it's here. Yeah, it's here. Okay, because I need to give into R the path of the file. So the best solution is that I click on the right I click on the file with the right mouse and I take property. Property should give me the path. Okay, it's here. It's this one. Just 1 second. It's I cannot copy it, but I can paste it here. So it's C. Probably it needs the double slash into R. Let's see. No.
If you copy it from the file manager part, it will copy.
Ah, okay. It's
From the bar, request to download. Just press a little bit right of it. Right.
okay.
And copy item is not copy.
So you mean if I copy here?
Should we copy the whole thing?
Let's see. No, I don't think. No.
Maybe double pressing there.
Okay.
No.
I don't think so, but maybe just 1 second. Let's see here. Property, but yeah. Okay, now I can copy it, but probably I could copy it even earlier. And then I need to add the download. Let's see. Not sure about. Okay. It doesn't find it, so just 1 second. Because I think under Windows we need double slash. Yeah, now it's okay. Downloads, and this is called the name of the. Ah, okay. The slash should be okay. The name of the file. But I don't think it is this one. Ah, mooring forces. It is this one. Okay. Okay, there is. I think. Let me check. I think there is a mooring forces dot s.
Maybe it becomes the way of the selection to last.
Yeah, I'm probably it is this one, which is not okay. Let's see, just 1 second, because I need to enlarge here, otherwise it's impossible. Okay, let me just check source to use. Let me see, because I think mooring forces, R, mooring forces dot R. Yeah, okay, good. So I uploaded it in this case, and let's check with the list. You see that there is now moorings, and moorings is my function. Very good. Now, I think it is just enough that I type moorings. Let me see. Let's assign the result to a variable like a equal moorings. Let's apply the default. You see that it went. And what is the result? Let's see A. Okay. You see here it's the computation of the wind force, computation of the moment. We did this already, but the function remade it. And this is the strength, the forcing on each spring line. And these are the safety factors. I made a check of the equivalence of the forcing in the y direction, equivalence to the wind force, and also a check on the safety factors. So everything went fine. Now, in order, this is very, very blind what I did. It is something that I don't advise you to make in your profession, because applying blindly a software, it's not a good idea. It's not a good idea because the software may be bugged, and maybe that my software is bugged because I did it by myself. So the best thing is when you get a software to check and understand line by line what is done here. So let's have a look. We have 5 minutes to go and we can start. First, there is a definition of the name of the function with all the default values. So you should also check that everything is correct here. Now, here there is, this is an old address, I have to change it. Computation of wind force, this is something that we already did. Okay. Computation of rotational moment, positive clockwise, already done. And then there is the computation of the angles theta e, and it's just a trigonometric computation. It is something that we can understand easily, but it would be better to check it. Computation of the length of the mooring lines. And first, I have the length from bollard to chock, and this is done through the coordinates. You see, coordinates of the chocks, coordinates of the bollard. And then the total length, which is obtained by multiplying by 115. And then there are the steps that I already discussed, computation of the spring constant, Ki. This is a force cycle. It is repeated everything from 1 to 6. Okay. So here actually it's out of the 4. So this is, because this is valid for any spring line. So the cross area is valid for everyone. The spring component along Y is repeated. It's done just once. And then these are the next step, the KYI. And this is done by using a vector, because this is indeed, when you see squares in R, the squares identify a vector, and you have to put between square parentheses I would say this is a matrix because it has 2 coordinates. You have to put the coordinates, the index of the vector between square parentheses. When you see 2 coordinates, it's a matrix in 2 dimensions. with 3 coordinates. It's a matrix in 3 dimensions. Here, you see that before the first comma, there is nothing, which means that it's applied to the whole column of the matrix. And so the result here, what you obtain here, is a vector, actually. And then there is the next computation, and then we can compute A, B, and C. And then ship translation, etc., etc. And then here there is the check. So if mean fs is greater than 10, check safety is okay. And now there is the output. This is the last thing that I think it is useful that I tell you. The output is a list, which means that it's a cluster of results where each result is named. Into a list you have names. In fact, you may remember that here you see when I type A, which is the result of the computation, I have a list of several results. And the dollar means the name of each result. The dollar identified the name of each result, which I defined here. Py is equal to py. Py is the result of the computation of the vector that computes the forcing along the spring lines in the y direction. And then I have the remaining ones. And then I give the instruction to return the output. And so I get the list as a result. I leave to you the task. If you are interested, this is not something for the exam, as I said. If you are interested to look at how this function is written, and this would be an excellent training for you for R, I leave it to you. Any questions?
No, Prof. Thank you so much.
Thanks. I can stop the recording. Okay,
Thank you.